Hello everyone. I'm Hao. I'm going to present our work PECAM, which is a privacy-enhanced video streaming and analytics via securely reversible transformation. This is a joint work of Nanjing University, Cornell University, Microsoft Research, and Microsoft Azure for Operators. Video streaming and analytics systems are widely deployed to ensure the safety of people's life and property. A video streaming and analytics system typically consists of two main parts, that is, a set of front-end video sources and a set of back-end video subscribers. Front-end sources stream real-time videos to corresponding back-end subscribers via the Internet. But the convenience of ubiquitous video surveillance systems has also raised privacy concerns. In recent years, governments and institutions around the world have been introducing laws and regulations to regulate and protect the privacy and security of user data. The goal of our work is to improve the privacy of user data in the video streaming and analysis system. Here, we take the traffic monitoring scene as an example to explain the privacy protection requirements in the video streaming and analysis system. The leftmost video frame is the road video frame captured by the front-end camera. We can see that the video frame contains both the vehicle and license plate information. An ideal video privacy protection method should be able to erase all private information in the video frame in real time, such as the license plate number. Protected video can be encoded and sent to the backend, which supports human-in-the-loop inspection and intelligent algorithm analysis, just like the unprotected video. Once an abnormal event is detected, for example, a traffic accident occurs, the authorized party can directly recover the original video from the protected video. And the recovered video can be used as evidence for forensics. At the same time, the protection method should ensure that no unauthorized organization can reconstruct the original video from the protected version. In response to these needs, we designed a privacy protection system, PECAM. The PECAM system can meet the following requirements. The first requirement is to preserve the video semantics. The protected video should also be used for manual inspection and automatic algorithm detection. The second requirement is securely reversible. Only authorized people can recover the original video from the protected video, while the third requirement is real-time. The fourth requirement is bandwidth-friendly. Since the protected video will be sent to the back-end through the network for analysis, our privacy protection scheme does not increase bandwidth usage. Let's first introduce the related work of visual data privacy protection. We have classified the work that performs privacy protection on visual data. An intelligent video stream analysis system is demonstrated in the above figure. The first kind of work is the homomorphic encryption-based solution. In this method, the user data is completely analyzed in an encrypted state. This scheme can ensure the privacy of user data. Still, the deployment cost is relatively high, and the system performance efficiency is relatively low. The second type of work is privacy protection methods based on the trusted execution environment. The user data analytics process works in an isolated hardware environment in this approach. Therefore, the privacy protection scheme based on a trusted execution environment needs additional support, so the deployment cost is higher. The third part is a method based on model splitting. In this scheme, the first half of the video analysis model needs to be placed on the front camera to extract features from the video. The extracted features will be sent to the backend to complete subsequent inference tasks. However, the work based on model partition needs to put most models at the front end to achieve good privacy protection. So the security and usability are hard to balance. At the same time, because parts of the model are put at the front end, the risk of privacy leakage of analysis service providers is increased. There are currently three main categories of input transformation-based solutions. The solution based on ROI removal requires users to define private information manually, and use automated detection algorithms to detect and remove ROIs. The solution by adding non-adaptive noise to the data actually reduces user information according to the data distribution. Due to its weak adaptability, it isn't easy to take into account both effectiveness and usability. The seen adaptive solutions include attempts to automatically define and remove private information, which requires explicit privacy protection. The scheme we choose is to find the semantic information in the image and remove all the non-semantic parts to ensure user privacy. Next, I will introduce how we came up with 4 novel designs to meet these 4 requirements. The first technology is to achieve semantics-preserved privacy protection. We will break down this technology into 2 specific designs. The first design is to determine a privacy protection effect. We have analyzed the commonly used video analytics services, and we find that most video analytics tasks in the video surveillance scenario only rely on the category-level information of the object and rarely rely on the instance-level information of the object. Therefore, we design a specific privacy protection style and perform video privacy protection by transforming the video into this style. In the end, we chose a kind of cartoon-like non-photorealistic rendering, which can remove instance-level details such as texture and preserve the category-level information of objects, such as shape and color. At the same time, this style can maintain the video's semantic information, such as the spatial and pose information. The second technology is how to transform the video into this style automatically. This has many excellent technologies in the field of computer vision, such as the cycle-consistent generative adversarial networks. Naturally, a pair of generative networks, denoted as transformer and reconstructor, will be trained according to our privacy style. The transformer will transform the video into a privacy protection version, while the reconstructor will undo the video protection. However, the current cycle-consistent design is not secure enough to protect the video's privacy. Specifically, attackers can train a pair of transformer and reconstructor by themselves, and then use their own reconstructors to undo the protection performed by any other one. Therefore, our second technology is a securely recoverable video transformation algorithm. In this technology, we introduced a secret mechanism, which ensures that the privacy protection style generated by each video protector is the same, but the specific protection processes are different, which ensures that only the reconstructor paired with the transformer can reconstruct the original video from the protected version. In this technology, we also use the visual similarity loss to improve the network training performance. The SSIM loss will make the reconstructed video and the original video in a high degree of visual consistency. Compared with the pixel-level measure L1 norm, the visual similarity loss function can provide a better reconstruction effect in our scenario. The third technology is proposed to realize real-time protection at the front end with limited computing resources. First, we designed a lightweight network structure for the transformer to achieve faster protection. Then, we make full use of the temporal locality of the video to dynamically determine whether the current frame needs to be quickly protected. Since the purpose of reconstructing the video is for forensics, such as identifying the suspect, we may not need to reconstruct every video frame. We design a lighter video protector named Fast Transfer by model distillation. The video frames protected by Fast Transfer are not reversible, but the protected frames are visually consistent with the frames protected by transformers. We designed a heuristic algorithm to determine whether the current frame needs to be reconstructed. If it needs to be reconstructed, the current frame is handed over to the transformer to perform protection. If it does not need to be reconstructed, the system will forward the current frame to the Fast Transfer distilled. Through the alternating work of these two networks, the system can achieve real-time protection with limited resources. The fourth technology is how to encode the protected video, so that privacy-protected video takes up less bandwidth. If we use traditional video encoding algorithms, such as naive H.264, to encode video, it will seriously compromise the reversibility of video frames. This is because the video encoding algorithm will remove high-frequency noise that is not easy for a human to detect from the video frame. However, this high-frequency information is more important for the reconstruction of the original video. Here we adopt two strategies to encode the video. The first strategy is encoding the reversible frames through a lossless algorithm and encoding the non-reversible frames through a lossy algorithm. By doing this, we can reduce the bandwidth usage during network transmission without damaging the video's reversibility. At the same time, we also need to make the adaptive removal of the high-frequency information in the reversible video frame. That is, we erase some high-frequency noise that has little to do with the reversibility of the video so as to reduce the bandwidth usage further. This is the workflow of the PECAM system. The workflow of the PECAM system can be divided into two phases, namely, the preparation stage and the in-use stage. In the preparation stage, we can train a pair of reconstructors and transformers through the specific style we set and the security-reinforced cycle-consistent generative networks. We then use model distillation to obtain a lightweight video protector, FastTrans. During the in-use stage of the system will determine whether the current video frame should be protected by transformer or FastTranser according to whether the current video frame needs to be reversible. No matter whether the frame is reversible or not, it will be encoded by the compressor. The encoded video will be transmitted to the back end through the network to be used as the input of some tasks such as human-in-the-loop inspection, automated algorithm analysis. Once the abnormal event is detected, the authorized party will reconstruct the original video from these reversible video frames as evidence for forensics. Given our security model, we analyze the privacy enhancement of PECAM. Here we try to answer is much more difficult for an adversary to indirectly obtain the VSAP information by reversing the transformation in unauthorized manners. We analyze the feasibility of launching the two attacks and conduct experiments to support our analysis conclusions further. In the first attack, the adversary ignores the existence of a secret key and attempts to train an RGB2 RGB transformation with public available resources like training data and neural architectures. In the second attack, the adversary randomly chooses a secret to train another PECAM reconstructor. We conduct comprehensive experiments and analyses and show that the two possible attackers, in reality, are difficult to undo the privacy protection. That shows the security of our method. Finally, we also conducted a comprehensive performance evaluation of the PECAM system. First of all, we found that the detection accuracy of the protected video can reach 96% of that of the original video. In terms of privacy enhancement, we find that it is difficult for attackers to extract private information from videos, whether by directly extracting private information or indirectly reconstructing the private information. In terms of bandwidth usage, under the same reconstruction effect, our video encoding design can improve the bandwidth usage efficiency of naive H.264 by 1.8 times. In terms of system performance, we can run in real time on the front-end camera. Compared with the baseline methods, the system performance is improved by 12 times and 46 times. Here is a demo of the PECAM system. We can see that the leftmost video frame shows the video captured in the indoor monitoring environment. Both the private information, such as face detection, and non-private information, such as pedestrian tracking, can be analyzed from the video. Once the videos are protected by the PECAM, we can analyze non-sensitive information on the protected video, and the sensitive instance-level information is removed from the video. Here we summarize our work. We propose a VSAP enhancement system featuring a GAN-based video transformation PECAM. It runs on the VSA front-end to enhance whole-frame privacy over real-time video streaming. Its outputs can be directly taken as inputs by various existed VSA tasks in the backend. PECAM also makes transformed video securely reversible in the presence of an adversary. We believe PECAM's design is generic enough to become an intelligent platform hosting future privacy solutions for video streaming and analytics. Thank you very much for your listening.